Okay, this is lesson 5.4, Fundamental Theorem of Calculus, part 1. We've already done part 2, now we're going to go to part 1. What it says is if you do the, what's that symbol right there, d over dx stand for? Derivative. And what's this symbol here? Integral or antiderivative symbol, yeah. So you're doing the derivative of an integral. The derivative of an antiderivative is kind of what you're thinking about. Now it's actually a definite integral because you have a definite starting point and stopping point. All right? Now, and our function here is f of t. F of t is this curve. If we ignore the derivative and just looked at the integral, what's the integral tell you about this picture? It tells you the what? It tells you that area, right? Now, what does a derivative tell you about something? Slope, or how fast the function, the rate of change. Another word for slope is rate of change. The derivative tells you the rate of change. So if we do the derivative of this area function here, this is an area function, it tells us the area, it's going to tell us how fast the area is changing. Okay? A represents a constant. That's kind of like your starting line. X is a variable, so it's going to vary. If X is getting larger, if X gets larger and moves this direction, what's going to happen to that area? It's going to get larger or smaller? Larger, yeah. If this is my area, my integral, as X gets larger, the area is going to get larger, isn't it? So, unless of course this was below the x-axis, then you'd be getting more negative, a bigger negative value, not bigger negative value, but a more negative value. So, anyway, the derivative is going to tell you how fast this area or how fast this integral is changing. And the formula that you're going to use for it is what you're going to do is plug x in for t. So you're going to let x equal t, or let t equal x, in other words. So instead of f of t, this is going to equal f of x. And then the derivative of t with respect to x, we're doing the derivative with respect to x. So that means do the derivative of t is going to equal the derivative of x with respect to x, which would just be 1. So how come I took off? Here's the answer I have. What happened to these two symbols? Why are they gone? They cancel each other out. One's a derivative symbol, one's an integral or antiderivative symbol, so they undo each other. Kind of like multiplication and division, that type of thing. All right? So let's move over to number 38 off of assignment 5.4. And we're going to do the derivative. So the derivative of y would be dy over dx. So I'm just doing the derivative of y with respect to x equals, on the right side I'm going to put my derivative symbol, d over dx, integral from x to 1 over t dt. And x has to be greater than 0, but we won't really worry about that right now too much. Now the one thing you have to have is you have to have the starting line on the left. Your constant has to be here. Okay, when you run a race, for example, and someone wants to measure how fast you're going, the starting line has to stay put. Wherever you started at, it can't move. If you're trying to run the race, you're trying to run 200 meters, and the starting line keeps following you, and you just can't get 200 meters away from it. That'd be frustrating, wouldn't it? That's kind of what's going on here. Your starting line's a variable. This is your starting line. This is your left is your starting point. So this is your starting point here. So we don't want that to be a variable. We want that to be a constant. We want your starting line to be a constant. Okay? So how could I switch these two? If I switch those, I just have to do a what? A negative. Yeah. So I'm going to do that. I'm going to switch those. So dy over dx, my derivative of y with respect to x, equals, and let's just put the negative out front. Negative of the derivative of the integral. You can switch those from 1 to x. Now we're ready to do the problem, really. Now we're going to let t equal x. You're always going to let t equal your upper bound. Okay? So let t equal x. So the derivative of t, dt means derivative with respect to x, is going to be the derivative of x with respect to x, which is just 1. So your answer is going to be this. The derivative of y with respect to x equals the negative of, what's going to happen to these two symbols? Cancel. Plug an x in for t, so you're going to have 1 over x times dt. What's dt equal to? 1, so we'll just leave that off, times 1. That's your answer. That's your derivative. That'll tell you how fast that area is changing. Let's do one more before we stop for questions. Is our starting line a constant? Is the lower bound, the left boundary, a constant?
Yes.
Yes, it is. It's 0. So we can go ahead and start this problem right away. The derivative of y, so this is my symbol for derivative, d over dx. It's the derivative with respect to x. The derivative of y, so I'm going to have a y right there. On the right side, I make that same symbol, the derivative with respect to x, from 0 to 2x, cosine of t dt. What should I let t equal this time?
2x.
2x. Yeah. T will always equal your upper bound. Okay. So dt, the derivative of t, is going to be, what's the derivative of 2x with respect to x? What's the derivative of 2x? 2, just 2. Okay. So now we start plugging stuff in. dy over dx equals, what's going to happen to these two symbols? Cancel out. Plug the 2x in for t. So you're going to have the cosine of 2x times the derivative of t. What's dt? 2. That's your answer. Any questions about that? It's really just a matter of plugging in your upper bound in for t and then multiplying by the derivative of that upper bound.